next talk will be by Romain Brette. So let me see. Yeah, Romain, you are there. That's great. So let me give a quick intro to you. So Romain Brette is a theoretical neuroscientist in Paris. Great, the screen sharing also works. And he has worked in cellular biophysics and systems neuroscience, specifically on modeling auditory perception, and who has done also a lot of reflection on the foundational concepts of neural modeling and computational neuroscience, such as neural codes, computation, and information. Okay, so yeah, when you are ready, the stage is yours, Romain.
Okay, thank you. Can you hear me well?
Yes.
Okay, perfect. Thanks. Thank you for the invitation and the introduction. So, so this talk is going to be I guess, a critical look at the idea of neural computation. So, as an introduction, I just want to say that I'm myself a computer scientist by training. I learned theoretical computer science, computability theory, complexity theory, Gödel's theorem, and etc. and so on. So it's with all of this in mind that I started my research, my PhD in computational neuroscience. And for a while, I used to say that I try to understand how the brain computes. It didn't come to my mind to ask whether the brain computes. And that's not a very scientific attitude, if you think about it. If the claim is not completely empty, then computation is a scientific theory of brain function. So what we should do is first clarify what this theory means, and then actually examine whether it's empirically correct. So what are we talking about? I'll start with a classical example of neural computation, which is navigation. So desert ants, for example, they can look for food. They wander around their nest, and then when they find food, they return to the nest in a straight line. And what's extraordinary about this behavior is that they don't use visual landmarks. It seems that, well, they must represent the position where they are, something like that. So let's say that the ant finds some food at some time, t, and then it would return to its nest in a straight line, so along a vector, which I'll call the homing vector, x. Now, suppose that actually it didn't find food at this time, but a later time, and then it comes back to the nest. So the homing vector would be another vector, but it's these two vectors are going to be related in a very simple way by the displacement of the ant. So that's the velocity vector times the time interval. And so because the behavior has this particular structure that the ant always goes to the nest in a straight line, you have a mapping which takes the homing vector at a given time and maps it to the homing vector at a later time. And it turns out that this mapping is a simple calculation based on two things that you can measure behaviorally, which are the homing vector and the velocity vector. And so now this mapping can be iterated from the nest to the final position. And what we get is a computational model of behavior with an input, which is the velocity vector as a function of time, and the output, which is the homing vector. And that computation we call path integration. So here you have an example of computational structure in behavior. But so far, I have talked only about behavior, it's just a description of behavior. I haven't talked about the brain yet. So the second step is to say that, well, the ant actually has a brain. And since it uses its brain to do that behavior, the brain must implement this computation. What does it mean to implement this computation? So the standard interpretation that you will find in many papers and books, philosophy in particular, is as follows. if we consider that the future behavior, so the actions of the animal, is determined by the state of the brain at a given instant, then there must be a mapping from the state of the brain at that moment to the homing vector. And so we say that the brain represents this vector x and also the velocity vector at any time. Now, two successive states must be related by the dynamics of the brain. And so what it means to say that the brain implements the computation is that the diagram commutes. That means that when the brain goes from one state to the next one, the variables that the state represents go through one step of the computation. So in this description, you recognize some familiar concepts of computational neuroscience, and in particular, the 3 levels of MAR. So you have the algorithmic level, the implementation level, and in between, you have representation which bridges the 2 levels. Now, this reasoning is pretty solid, but the main issue, as you will see, as I will discuss mainly, is what we call the neural state, what it is exactly. But before that, I first want to raise an important loophole in the reasoning. So it's an example which I took from philosopher Farid Zanoun. There's a completely different way to solve the path integration problem. It's not at all what the ant does, but it's something that you could do. You take a rope, you attach it to the nest, and then you take the rope with you. When you find food, you pull on the rope, and when it stands, you just follow up the rope to the nest. And you arrive to the nest in a straight line. So behaviorally, if you just look at the trajectories and so on, that's exactly the same as the ant. And that implies that everything that I've described in terms of behavior, this computational structure, is still there. But I don't solve the problem in the same way at all. So it would be an error, in fact, to call this a description of behavior. That's where the problem is. Because in reality, we are not exactly describing the actions of the animal, or of me, with the vector x, but the result of those actions in the environment as observed by us. So in the case of the ant, the homing vector actually corresponds to a particular motor command. But in the case of the rope, it does not. It actually corresponds to the direction of the rope. But the action that I'm doing is always the same. I'm pulling on the rope. So I'm not actually computing the homing vector. I'm solving the problem, but I'm not doing the calculation of this homing vector. So it's the results of my action that have a computational structure, but not my actions. And it follows that the rest of the reasoning collapses because in this case, the brain, my brain, does not in fact represent the homing vector x because that vector is in the environment and not in the actions of the organism. And so the brain does not in fact compute the homing vector. The way I solve the problem here is not by calculation. So more generally, not all problems that we solve are solved by calculation. Simply because all problems are not information processing problem. In this case with the rope, I don't treat the problem as an information processing problem, which is to map an input vector to an output vector. I don't do that. I just interact with the environment. So in some cases, behavior does not necessarily involve computation. So that's the whole point of embodiment theories. Now, of course, that's not what the ant does, because we know that if you move the ant to another place, then its homing vector direction will be unchanged. And that is what philosophers like to call representation-hungry behavior. So I'll assume that the behavior of the ant is actually of this kind, and it does have this computational structure. And now we'll move on to the question of neural states and so on. So recall the reasoning. If the brain state determines the actions of the organism, and if indeed the velocity and the homing vector are properties of the actions of the organism and they're not in the environment or in the interaction, then there must be a mapping from the brain state to those properties. And so that means that potentially you could read in the brain the position of the organism. That's correct, but we really haven't said much when we say that, because if brain state encodes all future behavior and action, then the same vector, the brain state, also represents lots of other things, like a shopping list that you have in mind, for example. Now, that is not at all a symbol in the sense of the computational view of mind, or in the sense of a variable in an algorithm, because the variable in an algorithm stands for something in particular. So in the idea of a symbol, there is necessarily a form of reductionism. That is, that there's a subset of the brain that represents a variable. And that leads us to the standard idea of neural computation and neural representation, where it is a neuron or a group of neurons whose activity plays the role of a variable. And typically, the method in neuroscience is to exhibit a correlation between some property in the world and the activity of a neuron or a group of neurons. The problem with that is that typically the activity also varies with lots of other things, which are not necessarily tested in that experiment, such as other features of the stimulus or other stimuli or the context or what the animal is trying to do and so on. So in fact, in general, those activities that are identified in the brain do not have the quality of symbols, things that could be used in an algorithm. So all this is explained in more detail in my paper on coding, so I won't go in more details. And I really want to focus today on the notion of neural state, which is a critical point. So remember the key idea: the brain is a physical object. It's in a certain state, which characterizes that object, characterizes the brain at that moment, all you can ever know about the brain. And that state must predict the actions of the organism. So that implies that from the state of the brain, well, you can map it to the homing vector and other things. So that's the idea of a state. And of course, you have this idea in physics. For example, you take a ball, it has a state, which would be in mechanics, its position and speed. So that if you know the position and speed of the ball at this time, then you can predict the trajectory. And that is what a physical state is. It's a set of properties at a given moment that completely characterize the future behavior of the object or the way it might interact with other objects. A computational state is something like that too. But now comes the confusion, because what people typically call a neural state, practically in neuroscience, is not this kind of thing. So here's one example, but it's very typical. You count the number of spikes produced by a neuron between 300 and 1,000 milliseconds after the presentation of an image. And this count is then considered a representation. But this measurement is not at all a state in the sense that I discussed just before. And therefore, it cannot be in correspondence with a computational state. It's not a state, it's a temporally extended measurement of brain processes at a fixed time after the stimulus. And that's why we call it neural activity. It's some activity, it's not a state actually. It's a count of historical events that occurred during an experiment, not a state in the sense of a physical or physical state. So now when you try to fit this with the computation model, it doesn't work at all, because this is not a state, but a measurement, so it doesn't undergo dynamics actually. Properties of a process are abusively called a state so that they can be said to be updated by neural dynamics, but that's false. Properties of a process are not themselves updated by the very same processes. Neural activity is not a computational state. So the diagram is never going to commute. Now, the only way to make this work, you can make this work, is by having the iteration map the measurements of some neurons to some other neurons. And this is what is done in feed-forward networks, in deep neural networks, for example. But this trick doesn't apply to the brain. Neurons are coupled, and the output and input are also coupled through the body and the environment. So when I wrote my paper on the neural coding metaphor and the abuses in the neuroscience literature, perhaps the most common objection I got was that I was attacking a straw man. Yeah. So when people say that a neuron encodes the orientation of edges, all they mean is that there is a correlation between a stimulus property and its activity and nothing more. You know, people would say that they don't mean more than that, that it's causal or that it's state or things like that. Well, that's demonstrably false if you look at the literature, and that's what I try to show in the paper. But what's interesting is that, on the other hand, philosophers of cognitive science, and I gave a few examples of representative papers, on the other hand, they seem to take those loose claims for established scientific facts. Neuroscientists really have established that there are neurons whose internal state correspond to some mental property. But apparently they're not aware that neuroscientists use words such as neural states and codes and representations with little care. So most philosophers agree that to implement a computation is something like this. That is, that transitions between neural states map to transitions of a formal algorithm. So you would see that in Chalmers, Putnam, Searle, and so on. But what they apparently don't know is that what neuroscientists call neural states are in fact not states at all. They're already properties of the processes. So they can't be again subject to brain processes such that that would correspond to transitions in an algorithm. So to conclude, well, does the brain compute? Well, some aspects of behavior have a computational structure. So I give one example and there are others, but not all behavior is computational. And neural dynamics more generally is not, well, it's not generically computational. So, and in particular, it's not obvious at all that perception is a computational process. It doesn't follow from any description of the dynamics of neurons. So thank you. I stop here and I'll take questions.
Okay, thanks a lot, Romain. We so far have no question in the Q&A, so anyone who wants to ask something can do so now. In the meantime, I do have a question, something I wanted to ask you. So I think, so one thing you generally criticize, I think, is that something like something we consider to be a psychological unit, something like the perception of a face, for instance, doesn't need to correspond to specific to certain neurophysiological states. So, for instance, to specific neurons or groups of neurons. So my question is, what would be a general way forward? Is that a very hard problem to tackle? Do we need some, I don't know, some very new idea about how brain and cognitive processes relate to each other? Or is there some direction one could take to make a solution more likely?
Oh, yeah, thank you. It's a difficult question for which I don't really have an answer. So mainly what I wanted to do is to point out that this inference that we make implicitly is well, has no logical basis, basically. Well, okay, there is one general comment that I can make, is that there's this tendency that we have, and I think many people, I guess, in philosophy have pointed this out, the tendency that we have to reify mental states. That is to say that, you know, a percept is some kind of thing in the brain. But a percept or a mental state is not a kind of thing in the brain. It's an activity of the brain. If your brain stops, you don't perceive. So it's not it's not actually some state, in fact. That's also one confusion that there is here, that is maybe due to language, really. that we use those concepts, or even the terms mental states, that is very misleading, as if it were a state as a physical state, like position and speed of a ball, for example. But a mental state is not that. It's state in the sense of a mood or disposition or something like that. But it's actually not the state of a physical object. It's more, like maybe an activity, something like that. So you're not going to find it either in the state of a neuron or even, I think, in the state of the brain, because it's not a state in the sense of the physical state. So we use this term, but it's very confusing, in fact.
So would a more dynamical approach generally be better to those kind of things?
I think a dynamical approach would be better for sure in general when we, in general in biology, because biology is about processes in the brain and elsewhere. So even, I mean, in neuroscience, if you look at the models, and I mean by that the biophysical models of neurons, and those are dynamical systems. Physically, those are dynamical systems. Those are not computational systems. And on top of that, we try to make them congruent with computational systems, but that's secondary. And that is motivated by, some computational structure that we may find in behavior sometimes. But it's secondary. If you look at the biological processes themselves, they are not computational processes primarily. They are, dynamical systems. So yeah.
Okay.
Of course, to say that the brain is a dynamical system is kind of a triviality. So that's certainly not sufficient to address it.
Yeah, I understand. So it looks a bit like a hard problem really to tackle.
But I mean, who said it was going to be easy?
Yeah. Okay, yeah, thanks a lot. I'm looking now at the questions posed in the Q&A. There are a few of them. So one upvoted question is, what do you think can be what do you think can be called as neural states? How can we measure them? Do you also think neural states actually represent anything other than themselves?
You mean what examples of neural states? Is that the question? Or
yeah, I'm not so sure I understand it myself. So
I mean, I can give an example of what we were saying. I mean, we know what it is. It's in actually you find them in the biophysical models. So for example, physical states would be a membrane potential, calcium concentration, this kind of things. These are states in the physical sense. What is not a state is the number of spikes in a given interval. That's actually a count of historical events associated to a system. That's not a state. So you have states, that you could take membrane potentials and so on. But
yeah, I think this is probably what the first part of the question meant. Then the second part was, do you also think neural states actually represent anything other than themselves?
Okay, yeah, that's a good question. That's a bit related, I think, to your question too. Is the so again, that's the idea of reification. The idea that when we say that we represent something like some image, for example, when we imagine, we represent to ourselves the face of someone, for example. Well, we say that there is a representation in the brain, but it's a word that we use, but it doesn't actually correspond to a thing in the brain. The image is not actually in the brain. What we mean by that is that we are in the activity of representing to ourselves the image. So if we're looking for a neural state that represents that image, we might be just fooling ourselves, because if what we're looking for is an activity, we're never going to find it in a state. So this comes from the confusion about what it means to represent. And actually, there's a paper from Farid Zanoun that I mentioned earlier on exactly this. confusion, the reification of representation, that we take it as a thing where actually it's an activity. Mark Bighar has worked on that too. Representation is something that we do, not something that we look at. Okay.
Okay. Yeah. Another upvoted question from the audience is, okay, someone is asking, if all behavior is not computational, would it be possible to mimic behavior artificially using pattern recognition of the brain activity? If so, to what extent would it be possible? I can read it again if.
Okay, I mean, yeah, I'm not entirely sure of the question, but you know, I gave an example of a non-computational behavior with the rope. Okay, so there are two things here. You could very well imagine a robot who would pull on the rope and do exactly this behavior. The robot will have a computer inside it, and we probably use it to pull on its levers and so on. So you could reproduce the behavior, except this behavior would not involve actually calculating the homing vector. So there would be some computation involved, but not the computation of the trajectory, in fact. So that's one thing. And then there's the second thing, which is the relation between computation and simulation, or modeling and simulation. So if you take, well, dynamical systems in general, dynamical systems are not necessarily computational systems. Computational systems are certain kinds of dynamical systems. But you can simulate dynamical systems, though. You can simulate the Hodgkin-Huxley model, you can simulate all sorts of systems. But those are simulations. So the fact that, or the brain is, or the dynamics of the brain are not necessarily computational doesn't imply that you can't simulate it. That makes sense?
Yeah, so you would say that it is possible to mimic artificially.
I wouldn't go that far because I don't know.
Yeah, okay, I see.
The lucid answer to this question is I don't know. Maybe it's possible, maybe not, but
okay.
There are arguments that it's not possible, but I don't know. Okay, I'm agnostic on this. Need more thinking about that.
Yeah, I see.
I would say that if you can model that, okay, one partial answer to this question is that if you can model it as a dynamical system, like a conventional dynamical system, then you should be able to simulate that dynamical system and therefore to reproduce it. But the question then is whether the brain is or can be modeled accurately or in all its features by a conventional dynamical system, and that is might not be that obvious if we looked at the biological side of things. And I'm thinking specifically about how a cell works and the fact that it's not clockwork work. So I'm not sure I can really answer this question. I would say that within the framework of dynamical systems, so the cybernetic framework, basically, that should be possible. But if we go beyond that, I don't know.
Okay, thanks a lot, Romain, for your talk.
Thank you.
That was great. So you can have a look at the remaining questions in the Q&A. Feel free to answer those.
Okay.
So thank you.
Thank you.
The next